The other day we were discussing how you can make feedback systems with op-amps. At the same time, to make the op-amp behave like an integrator, it has to be biased in the correct region. Okay? So whatever feedback network you have to do your signal processing function must also provide DC negative feedback around the op-amp. Okay? We took this circuit as an example. So again, I'll write the more complicated circuit with single supply, but since that's what we are going to use, it will be better to do this, at least for now. Okay? So we have V in plus V bias. This is tied to V bias, and let's say this is R and K minus 1 times R. Okay? So if you evaluate what appears at the input of the op-amp because of the feedback network, when mean equals 0, what is it? It will be V bias minus V out by K plus V bias times K minus 1 by K. Okay? Which basically means it is V bias minus V out. So this is evaluated, of course, with the proper sign, with the plus from the plus input of the op-amp to the minus input. So now, when you evaluate it, the part that has V out must have a negative sign. That's the meaning of DC negative feedback, right? So VID versus V out, this must have a negative slope. Okay? So if you plot V out versus VID, because of the op-amp, the characteristics will look something like this. Okay? There will be saturation, and when VID equal to 0, it goes through some point. Now, this VID versus V out must have a negative slope, and not only that, it should intersect the characteristics at the correct point. So in this case, if you plot V bias minus V out, so you want to plot VID equals V bias minus V out, right? Sorry, V out, is this correct, or V out by K? So V out by K, right? So this was and the same thing is here as well. Okay. So if you plot that, what is it going to be on the same axis? You can of course write it as V out equals V bias minus K times VID. Okay, this is what VID is, the DC part of it. Okay, so it will have a negative slope of K, and it passes through the origin at V bias. Okay. So the op-amp will get biased somewhere close to V bias because the slope of the op-amp characteristics is very high. Okay. So instead of this, if we had a slightly shifted characteristic, because of the offset, the bias point will still be close to V bias. The bias point is the intersection of the op-amp characteristics and the feedback network characteristics. Okay. Now the feedback network by itself crosses VID equal to 0 when Vout is V bias. Okay. Now because the characteristics of the op-amp have a very high slope, even though it is different from V bias, it is not very much different. Okay. So you have to choose a certain bias point for the output, and you have to make sure that your feedback network will give you that characteristic. That is, it will intersect the op-amp characteristics at that bias voltage. Okay. Now what happens is, because you have negative feedback, even if I shift the characteristics back and forth a little bit, the actual bias point does not change too much. Okay. So any circuit that you make, you have to ensure that this is true, right? Is it okay? So let's take two circuits. Okay, now I am not going to draw the bias, but I think you are familiar enough with ideal op-amp circuits to tell me the transfer function of this. What's the transfer function of this circuit? What is the transfer function? No, what is this? Yeah. So it's the admittance of this branch multiplied by the impedance of this branch, right? So it is okay. So it has some transfer function, it doesn't matter. But is there DC negative feedback around this? There is. Okay. That's because you can see that at DC this drops out and some fraction of V out will appear, some fraction of V out will appear at the input. Okay. What about this circuit? What is the transfer function if it was an ideal op-amp? 1 over SCR, minus 1 by SCR. Actually, this is also minus, right? Minus 1 by SCR, but there is no DC path from the output to the input. So there is no telling where it will get biased. Okay? Depending on the offset of the op-amp, it could have been saturated, even if you apply V in equal to 0. Okay? What's the transfer function of this? Minus R by SL. So it is similar to this, meaning it's also an integrator. Is there DC negative feedback here? There is. Are you sure? There is. Why do you say no? So if I apply Vin equal to 0, there will be no voltage across this, right? So there is no DC negative feedback here either. What is the DC gain of the feedback network? The feedback network is this one, right? So there is no DC negative feedback here either. So you can't make these circuits, at least you can't make it in this form. Perhaps you can get this, you of course use integrators and filters and so on. So what happens is there will be some other network which probably has some feedback to this point, okay, which provides DC negative feedback. Just by themselves you can't make these circuits, okay, because it won't get biased properly. So the only way to do it is to have perhaps approximate it by having a very large resistor which provides DC negative feedback but perhaps can be neglected for the signal picture, okay. So you can evaluate in more complicated circuits how whether there is negative feedback or not, and it has to have negative feedback, otherwise it doesn't work. I mean DC negative feedback. This is true for every circuit. I mean afterwards we will make our circuits using transistors and so on. So every transistor has to get biased, which means that there has to be overall DC negative feedback around a high gain circuit like this, okay. So and also there is the question of if you have multiple op-amps, it's not immediately clear which way the signs must be, okay. So for instance, let's say I have a circuit like this. So just from designing the signal processing circuit, I don't need to put any signs because I know that this is a virtual short. The input of the op-amp is a virtual short, okay. So you can go and try it out. What will be the transfer function from between the input and output? Anyway, you go and try it out and we can discuss it day after tomorrow perhaps. And also which way to assign the signs to the op-amps, okay, both of them. So when I say what is V0 by Vin, I obviously mean that you assume that it's an ideal op-amp, in which case you simply assume this to be a short and this to be a short virtually, okay. But for it to behave like a short, there has to be DC negative feedback around each of the op-amps. So then you figure out which way the signs must be to get DC negative feedback, okay. So the bottom line is you use the op-amp as an integrator to complete your feedback networks, but you have to make sure that the op-amp is biased in the correct region, which means that it has to have DC negative feedback, meaning whatever feedback network you choose around the op-amp should provide VID versus V0 with a negative slope, okay. And it doesn't necessarily always have to be a straight line. It doesn't have to be a straight line. I mean, sometimes you can have a nonlinear network around the op-amp, in which case you get some nonlinear characteristics for VID versus V0 through the feedback network. And it's enough if it has negative slope and intersects the op-amp characteristic at the right point. It doesn't have to be linear. What I mean is it would have been fine if the characteristics were like this also, okay. Any questions? So prototype negative feedback system is like this. Okay. Sorry, this is 1 over k. So this is V out by k. So what appears at the input of the integrator is V in minus V out by k. Okay. Now this doesn't always have to be the case. It doesn't have to be just V in minus something. So in general, we can think of this entire thing being part of the feedback network. Okay. Sorry. So you have a network to which you feed V in and also V out, and that gets fed to the integrator. Okay. Now the input to the integrator can be of the form alpha in minus beta V out, where alpha and beta, where beta is positive, alpha can be anything. Beta is positive for negative feedback. Okay. Now the ideal solution to this is when the input of the integrator is 0. So that is alpha V in equals beta V out. Again, alpha and beta can also be frequency dependent, right? So that's how you calculate the transfer function. What I am trying to say is at the input of the integrator, you don't have to see V in with unity gain. It can also be multiplied by some number. Okay. Is there some circuit that you can think of that does this? Some simple circuit that you are familiar with? So if you do this, what is the solution? What is at least the DC or the ideal opamp solution? If the ideal, in our case, ideal opamp means you send omega u to infinity, right? So for all frequencies, the voltage at this point will be 0. Okay. What will be V out? Huh? Alpha by beta times V in. What is the feedback fraction? Huh? Beta by alpha. What is the feedback fraction? 1 by beta, right? Sorry, beta. The feedback fraction is beta. Because at the input you get minus beta times V out. Okay. So all I am trying to say is the gain doesn't have to be 1 over the feedback fraction. Is this clear? So that's because the V in can also have some other factor other than 1. So in this case, the feedback factor is 1 over k and the gain is k. Okay. So this is the sort of the prototype negative feedback system, but in general the circuits you make will be something like this. So is there some circuit that you can think of, some simple circuit that follows this, where the gain of the feedback network is not, the gain of the closed loop network is not 1 over the feedback fraction? The inverting amplifier. Yeah. So what is the input to our integrator here? With this sign. What's the input to the integrator? So the voltage at this point will be linear combination of Vi and V0, and the weight will depend on the resistors. Okay. So, and VID is defined to be opposite of that, right? So, okay. So the coefficient of Vi is not 1. It is minus k minus 1 by k. Okay. And V0 does have a negative sign, right? Minus 1 over k. So it does have negative feedback. But what is the gain? What is the feedback fraction here? One by k. It's the same as in the non-inverting amplifier. What is the closed loop gain? Huh? Okay. So again, this is roughly like changing the zeros of the transfer function by applying the input to different points. Okay. You can change the numerator. But the loop has not changed. So for instance, I make a non-inverting amplifier, and in absence of the input signal, it will look exactly the same as this, right? So this is an inverting amplifier. And I'll write it similarly. Okay. So in both cases, the feedback fraction is 1 over k. Okay. But the closed loop gain, here it is plus k, here it is minus k minus 1. Oh, I wrote it the other way around, right? So this is the non-inverting, this is the inverting amplifier. Yeah. V out equals? Yeah. 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 No, that's not. So in this case, the input to the op-amp is what? No, that is with the op-amp. So what I wrote here is, this is the transfer function of the feedback network. Okay, this is the function of this one without the feed forward block. If I have a certain V out here, what voltage do I get at this point? That's what I wrote. And if you place the op-amp there, it will get forced to 0. Right? Isn't it? So this network N will provide me alpha Vn minus beta V out. And it will get forced to 0 if I place N in feedback around an op-amp. Okay. So that's how I get alpha by beta. And that is true here also, right? I get this divided by this. Is that okay or no? I think, what was the question? I thought the question was, I don't get alpha by beta in this case. Yeah, that's correct. Yeah. No, it is, right? Why do you say it is not? No, this alpha in minus beta V out is the transfer characteristic of the feedback network N. So at the output of the feedback network, which is the input of the op-amp, you get alpha in minus beta way out. And that will get forced to 0 if you place an op-amp with a high enough gain. Okay. So, that's what is happening here also. So, in this case, this is, let's even forget the op-amp. Okay. Let's say we didn't have the op-amp. Just this network will give me VID equals something. VID is some voltage. Now, I make VID the input voltage of an op-amp and drive V0 from the output of the op-amp. In that case, this will get forced to 0, right? In the ideal case, when the gain is infinity. In the real case, you can say that VID is the output voltage of the op-amp divided by some quantity. Okay. So, in this case also, if you see, it is alpha by beta. Is that okay? So, again, even by changing the location of the input, you can get different outputs and also different transfer functions. And by changing the location of the output also, you can get different transfer functions. Okay. The loop gain is the same for both the cases. The loop gain only depends on the circuit when with the input shorted. And it's the same, right? So, I short the input here, this becomes ground, and I short the input here, this becomes ground. The two circuits are the same. So, the loop gain around the op-amp is the same. The closed loop, the loop gain is the same for both circuits. So, in this particular case, VID was what we had before. And here, okay. So, if I this is the same. The part of the output that is fed back to the input is the same. So, that means the loop gain is the same. But input goes through a different network in the two cases. So, you get a different gain. Okay. So, in both cases, before we had evaluated that the relative error in the transfer function will be 1 over the loop gain and so on. So, in both cases, the relative error will be the same, although the closed loop gains are different. Okay. Is this? So, what is the loop gain in this case? Let us say the gain of the op-amp is A0. Huh? A0 by K. And here? Also A0 by K. So, let us say A0 by K is 100. Okay. Now, your closed loop gain is supposed to be K minus 1 from here, K minus 1 here, and K in this case, right? So, in both cases, because the loop gains are the same, the relative error will be the same in the gain. Okay. So, what do you think the gain is going to be with a real op-amp? With an op-amp of gain A0, what will be the gain of this? Ideally, it is K. What is it with a real op-amp? So, we evaluated this, right? It's the ideal gain. 1 by reciprocal of the loop gain. 1 by 1 plus reciprocal of the loop gain. Okay. And what is it in this case? Ideally, it is minus K minus 1. So, what is it going to be? Same factor, right? Because the loop gain is the same, the relative error will be the same. So, and again this is true of AC as well. If you go to higher frequencies, all of these will become functions of frequency, okay, and these don't have to be resistors, they can be impedances. But if you use the same feedback impedance and same impedance from the negative input, in both cases the loop gain will be the same, okay. So, the transfer functions will have similar multiplying factors, okay. Any questions? So, the reason I stressed it was frequently it's common to say the closed loop gain is something, let us say 10. So, the loop gain is the gain of the op-amp divided by 10. But that is not the case here, right. Here the closed loop gain is not k, but k minus 1. So, it very much depends on the loop gain and closed loop gain are different things. The feedback fraction and closed loop gain are somewhat different. They don't have to be reciprocals of each other, okay. So, let us say we have something like this. Again, I will take this one. What is the closed loop gain of this, assuming an ideal op-amp? Huh? Minus k minus 1. What is it now? What is it now? Same. It is the same, right? In fact, with an ideal op-amp, you have 0 volts here. So, this resistor doesn't come into picture in the analysis. So, it is the same. So, let us take with R and without R. What is the actual loop gain? I mean, actual closed loop gain with an op-amp of gain A0? Huh? So, in this case we get, right, what is it in this case? What is the loop gain here? 2A0 by K. Why? K by 2A0. So, it actually improves. K by 2A0 is smaller than K by A0. So, this is better than this. With the extra resistor you are doing better. What is the loop gain here? What is the feedback fraction here? K by 2. Why? What is the feedback? I mean, what's the, so how do you evaluate the feedback fraction? You disable the input and you apply something to the output, see what comes back, okay, with the op-amp removed. What is that? It is, I mean, it's a simple voltage divider, right? It's R by 2 divided by R by 2 plus, huh? 2K minus 1. Yeah, so, right? So, what is this? So, this circuit is definitely worse, right? Because the extra term in the denominator is larger. And that's what you do expect. If you have impedances from this point, it is going to affect the loop gain. Although it does not affect the ideal closed loop gain, it does affect the loop gain. Consequently, it will affect the real closed loop gain. Okay. So, similarly, if you have capacitors here, it can affect stability and so on. Okay. So, if you have extra impedances from that point to ground, you will have greater problems with accuracy. Okay. Basically, you have a lesser loop gain, so you have worse accuracy. So that's pretty much all I had about the ideal op-amp. This was just to refresh some of the things that you should have already known all these things. It was to refresh that. Any questions on this? So the only thing that is left as far as ideal op-amps are concerned is the concept of fully differential op-amps. Okay. So with discrete op-amps, this is the kind of op-amp that you will use. You will have a differential input and a single-ended output. Now when you make circuits on an IC, there is some motivation to make fully differential circuits. Okay. That is, the output is differential and the input is differential. Every signal is represented by a differential signal. That is, it's represented by a pair of signals which vary equally in magnitude and oppositely in phase. Okay. So if you have a certain signal, let's say Vsig, it will be on 2 wires and ideally of this form. It will probably vary around some bias, but it will vary equally and oppositely. Okay. What's the motivation to do this? Why would you want to have fully differential signals? Common mode? Common mode noise will be cancelled. What do you mean by that? What's that? Yeah, so one thing is, if we are going to only sense the difference between the two, then a noise that is common to both the wires will get cancelled out. Okay. So let me show this. So let's say we finally process it differentially. That means that this amplifier is sensitive only to the difference between the signals. That is a condition, of course. The amplifier that you have following this must be sensitive mainly to the difference of the signals. In that case, so this is supposed to be plus V signal by 2, this is minus V signal by 2. Now you can get interferences from all kinds of sources, but let's say that it is some wire that is passing across the 2 wires. Okay. Some other wire that's passing across this. So it will have parasitic capacitances. Now if the layout of these 2 wires is symmetric, the amount of interference injected from this wire to each of the wires will be the same. Okay. So it will be some, let's say, Vn and Vn. Now if that is the same, when you process the difference of the signals, Vn will get cancelled out. Okay. So you should have differential circuits, but also they should be physically symmetrical. Okay. In that case, the common interference will get cancelled out. Now not only that, it's not just that this wire, this is interfering with these two. These two are also interfering with this. Okay. So what is the amount of interference? So let's say these 2 wires were carrying equal and opposite signals. What's the voltage on this wire? Okay. Let me call it V out because of the upper wire here. Let me call it Cc, and perhaps there is a capacitance to ground, Cl. What is the effect on V out because of the upper wire here? So it is Cc by Cc plus Cl times V signal will appear on this wire because of the upper wire. What about because of the lower wire? Negative of that. So it will get cancelled out. So it will, if you process a signal differentially, it is immune to interference that is injected upon it. It is also going to inject less interference because you have a pair of wires, each carrying equal and opposite signals. So if you have some other wire, from these two wires, the interferences will get cancelled out. Okay? Again, assuming physical symmetry and so on. So it is more immune to interference and it also puts out less interference. Okay? So the best thing is to make everything differential so that you have very little interference going around. And what little common interference there is will get cancelled out because you are going to process the signals differentially. Okay? Now that is an important thing that is left to the amplifier. The amplifier should be sensitive only to the difference. It should not be sensitive to the sum of the two signals. Okay? And as I mentioned earlier, that concept is the common mode rejection. So because of this, every signal is routed as fully differential signal. Okay? So that basically means that you will have less interference going around. Okay? So that is one type of thing. When you have interconnects, there will be less interference injected and also there will be more immunity to interference. What? Oh yeah. If you have both of these CCs, it will be, that's correct. So, because we have a network like this, from V6 we have CC and CL to ground, and we have another capacitor to minus V6. Okay. The exact expression will be CC by 2CC plus CL. Now there is another reason to use fully differential circuits. So I think you are familiar with this. You don't have to know too much about it, but the gate is biased at some value and then there is an increment Vi. Okay. What is the output signal? Minus GMRL Vi, and this is what we normally write. But a voltage is measured across 2 points, right? So across which 2 points are we talking about now? To ground. So let me call this ground. So across this you will have minus GMRL Vi increment. Is that correct? Plus some? Yeah, bias, that's okay. Bias I am not concerned about. What is the incremental voltage across this point and ground? Is that where you see GMRL Vi? Where do you see GMRL Vi in this circuit? Across the resistor. So, across this you will see GMRL Vi, and if you do have an ideal voltage source here, okay, there will be no increment between these 2 points. So, whether you measure the increment with respect to the top rail or the bottom rail, you will get the same answer. So, that is why assuming an ideal voltage source, you get minus GMRL Vi with respect to ground. Okay. Now, first of all, the source will have some impedance, which typically is some resistance and an inductance. Okay. And the line that is connecting to this circuit will also have some impedance. Okay. So the incremental current that is flowing through RL will also flow through all of this. So the actual voltage you see here between the drain node and ground will be minus GMRL Vi plus the drops across these impedances as well. So if you feed it to the following amplifier, you will get not only Vi but something else. Now in this particular case, this current is dependent only on Vi, but that's not always true. For instance, I could have a different circuit here, okay, that is completely unrelated to this, and it's extremely common. You have a single supply and you connect a whole bunch of circuits to it. So, the currents through these impedances depend on all kinds of circuits, which may not be related to VI. So, the voltage that you get at the output of a single ended amplifier can be corrupted by other signals. Is this clear? So, for instance, let us take just two amplifiers which have signals that are independent of each other. Okay? Let us say that this is biased at a bias current I1, this is biased at a bias current I2, and there is some impedance in series. And of course, by this I don't imply that there will be impedance only in the upper rail, there can be impedances in the lower rail also. Okay. What is the incremental current here? And let us say there is no circuit beyond this. What is the incremental current here? This is V1, it is GM V1, and let us say this somehow is V2. Okay. This is GM V2. Okay. So, if this is Z1 and Z2, so across this we have GM V1 times Z1, and across this we have what? So, maybe GM, so we have, in fact the GMs also can be different, right? GM1 V1 plus GM2 V2 times Z2. Okay. And the voltage across this is, the incremental voltage across this is, so let us say this is R1, GM R1, V1. Okay. So the voltage between this point and ground is what? Incremental voltage. So it is minus, GM R1 V1 plus GM1 Z1 V1 plus GM1 Z2 V1 plus GM2 Z2 V1. Okay, V2 rather. So first of all, it is not exactly GMR times the input voltage, and also it has some component because of V2. Okay. So if the following amplifier is sensitive to the voltage between these two terminals, its output will be in error. Now how much this error is depend on magnitude of Z1 and Z2, and as a designer, part of your goal is to minimize Z1 and Z2. Okay. But in reality you don't get ideal wires, so you will have some impedance. So this problem can be more or less bothersome depending on how you design it. So now the problem comes mainly because you don't know what the reference point for the signal is. In this case, you are getting GM1 R1 V1 across the resistor. Okay, but you are sensing the voltage between this point and ground. Okay. So the reference for the signal is not really used properly, or it's not known where it is. Okay. And because of impedances in the supply and ground lines, it's hard to find the exact reference point either. Now what happens in a fully differential circuit? Let us assume that these two are part of a differential circuit. You have V1 by 2 and minus V1 by 2. Okay. And there is some supply impedance here. Okay. And so on. And this is ground. What is the incremental current in this? GM1 V1 by 2, and here it is GM1 V1 by 2 in the opposite direction. Okay. So the voltage across this resistor is GM1 R1 V1 by 2, and across this in the opposite direction is the same. Right. Now if you measure each of these nodes with respect to ground, you will also end up adding the voltage drops across these parasitic impedances. Okay, parasitic means undesirable, something that comes there not intentionally, but because of the way physical characteristics of the circuit. Okay, but if you are sensitive only to the difference between these two voltages, what happens? What's the voltage? GM1 R1 V1. So although this, now the magnitude of this may be large, but it's not going to affect you because it's going to affect both the voltages in the same way. So it is like injecting a common interference. So the supply fluctuations will be common to both arms of the differential circuit. Okay, or at least you should design that it is common to, design it such that it is common to both arms of the differential circuit. Then when you look at the difference voltage, it will contain only the desired quantity, not the effect of currents through the power supply impedances. Okay, so this is a very strong motivation to use differential circuits. You can think of it as you are supposed to measure a voltage across two wires. Now normally you just specify one wire, assuming that the ground has no voltage across it. That is, there is a single point that is called ground. Okay, in reality you can't find it. That's why you have all these problems. So in a way, you are supplying the reference point for this signal along with the signal itself. Like each wire is the reference point for the other wire. Okay. So you have both wires across which the signal is defined, and it's defined accurately, more accurately than before. Okay. So this is a very strong motivation for making fully differential circuits. The reason something like this is not used in discrete circuits is cost, because you will end up with twice as many wires, twice as many components and so on. Whereas on an integrated circuit, the cost is not measured by the number of components, but the total area. Okay. So you can make, we'll see that afterwards, but you can make each of the components half the size, but double the number, then it doesn't make a difference to the IC. Okay. Now in fact, you are getting a performance advantage. So it is better to use something like this. So generally on an IC, you have fully differential circuits, and in with discrete component circuits, you will have single-ended circuits. Okay. But it is much harder to make single-ended circuits noisy, immune, and have very high dynamic range and so on, whereas it's much easier with a fully differential circuit. Okay. Any questions? So because of this reason, we have something known as a fully differential op-amp. I'll just introduce it. We won't discuss it further. Now, both the input and output are fully differential. So what does it mean? In the ideal case, these 2 points will be at the same potential. Okay. And the output can be anything, but it has certain common mode voltage that is defined. Okay. That's this common mode voltage, you can think of it as a property of the op-amp itself. When you are designing the op-amp, you design it for a certain common mode voltage. So the output voltage can be anything, but it will be fully differential. The value of Vout can be anything. If you think of it as an ideal op-amp, sorry, this is minus. Okay. So this is the alternative to something like this. And in the ideal case, you can assume VCM to be 0. I mean, just for simplicity. In reality, it will be some bias value. Okay. So the two outputs will be forced to go equally in magnitude, but opposite in direction. Okay. So this is a fully differential op-amp. By the end of the course, hopefully you will have learned how to make these things. Okay. Now with this, you can have op-amp circuits which have, in which all signals are fully differential. And this is the way normally circuits are done on an IC today. Okay. You don't use single-ended circuit unless there is a particular need. Sometimes what happens is you have to drive a single-ended output, like you have to drive a speaker. Then you don't necessarily make it fully differential. But inside the op-amp for signal processing, it is best if you make it fully differential. Okay. Any questions? So the only difference now is that the virtual short, of course, it's actually not a difference. There is a virtual short between the input terminals in case of an ideal op-amp, and the output is defined around a certain common mode VCM. The two outputs have equal and opposite swings. Okay.